Hi, I'm Jade. You may see me in the booklet as Dr. Jade Checlair, but I have not yet earned that title. I'm a graduate student at the University of Chicago, and I'm really glad to be here with you today. I hope the mic is working. Okay. So I'd like to talk to you about how we could test the concept of the habitable zone. In the near future, new and powerful instruments will allow us to characterize potentially habitable or even inhabited planets like never before. So what you're looking at here are a few instruments that are or have been, at least to some extent, focused on finding and characterizing exoplanets. However, so far, we have not yet been able to directly observe Earth-like planets orbiting in the habitable zone of their stars. However, as we look to the future, we can look forward to instruments dedicated to observing these kinds of exoplanets, which we think may host life. In particular, HABEX and LUVOIR right here, which you can see at the end of the curve, are two mission concepts that are in the running to become NASA's next flagship mission. And they're both direct imaging instruments, which means they would hide the light of the star to directly observe the exoplanets. And they're going to be focused on looking at these habitable Earth-like planets orbiting Sun-like stars. Oh, sorry, can you go back a slide? Okay, it's a little sensitive. So because we're going to likely have these new instruments that are going to allow us to observe Earth-like planets in the habitable zone, we're also going to be able, for the first time, to actually test habitability hypothesis. To do that, we'll have to use a statistical comparative planetology approach, which essentially just means that we'd be taking quick and cheap measurements on large sample of exoplanets to try and test for scientific hypotheses. So this way, we'd be taking the number and diversity of exoplanets as an opportunity. An example of that would be for us to focus at a given wavelength and try to detect CO2 on a large number of exoplanets to test a habitability hypothesis. Okay, now what I want to do with this kind of statistical approach is to test for the concept of the habitable zone. So the habitable zone is defined as the possibility of surface liquid water between two orbital separations. So usually, when a new exoplanet discovery comes out, especially if it's a terrestrial planet, it comes with whether or not it orbits within the habitable zone of its star. Here's, for example, an artist's depiction of the TRAPPIST-1 system. You'll see some planets closer to the star that are emanating water vapor out of them. Supposedly, what's going on is they're going through a runaway greenhouse effect. So they're quickly going to lose all of their oceans through space. Now, the planets that are further out here are just too cold to maintain surface liquid water. So it's really only between two defined separations that surface liquid water is going to be possible. Now, here's a slightly more scientific representation of the habitable zone. First, you'll notice that its size and distance depends as a function of stellar type. So we've got a sun-like star here where you've got Venus, the Earth, and Mars in succession. And the inner edge of this habitable zone is usually taken to be the yellow curve here. So planets that are closer in than this yellow curve are expected to be found in a moist greenhouse state, which means that they're hot enough that their atmosphere is going to be saturated with water vapor, and water vapor is going to be allowed to rise all the way to the top of the atmosphere. So hydrogen atoms are going to start to be lost to space. Now, the habitable zone itself, so the bluish region here, is assumed to allow for a functioning silicate weathering feedback on terrestrial planets. So the entire concept of the habitable zone is going to depend on this feedback actually functioning. So what is the silicate weathering feedback? Well, it's a feedback that relies on the cycling of CO2 in and out of a planet to maintain habitable surface temperatures. So for example, if you've got a planet that's orbiting a bit further away from its star, technically, its surface temperature could drop to below freezing. Now, luckily, as the surface temperature decreases, the weathering rate, so the intake of CO2 by the planet, also starts to slow down. So this is going to allow CO2 to build in the atmosphere of the planet through volcanism. And given that CO2 is a greenhouse gas, it's going to bring the surface temperatures back to habitable conditions. So this feedback here is assumed to be functioning on habitable exoplanets, so within the habitable zone. And we have pretty good evidence that it has been functioning on Earth throughout its history. However, we have no evidence whatsoever that it functions on exoplanets. We just assume it does. So let's come back to this slide right here. What's going to happen if the feedback doesn't function is this. So the outer edge is going to be brought much closer in, which means the habitable zone is going to be much more narrow. In fact, it's going to be unlikely for more than about a single planet to be able to orbit within it. So I'm going to come back to where the outer edge actually is. There we go. Now, the outer edge itself is going to be defined as the distance at which CO2 collapses out of the atmosphere. So it's too cold for CO2 to be maintained in vapor state. And so that means surface liquid water will no longer be possible because the silicate weathering feedback fails. So clearly, this whole idea of a functioning silicate weathering feedback is really important to the habitable zone concept and to discussing the habitability of any one given exoplanet. Yet it remains untested. Now, this is going to be important for migration of life in general, because if the silicate weathering feedback functions in the habitable zone, then it's going to be possible for multiple terrestrial planets to orbit within it. Because remember, if the feedback doesn't function, the outer edge is brought closer in. And if we have multiple planets orbiting within the habitable zone, it's going to also allow potentially for intra-system panspermia. So the exchange of life within one single habitable zone, so one single planetary system. But in addition to this, it's also going to allow life to potentially arise on multiple planets. So it's going to increase the chance of life being in any one given system because it can arise on multiple planets and then be exchanged within them. Okay, so the goal here is to test whether or not the silicate weathering feedback actually functions. So to do that, what we can do is take very low precision measurements of CO2 on a large sample of planets and see if we can detect a decrease in CO2 here on the y-axis with increasing irradiation on the x-axis. So to illustrate this, let's take the upper left point here. So you'll see it's a planet supposedly orbiting further away from its stars, so at a low value of irradiation, and therefore it's going to require a high amount of CO2 to maintain habitable conditions. Now, if we instead look at the point on the lower right, it's a planet orbiting much closer in, and therefore it requires less CO2 to maintain similar habitable conditions. Now, this is a purely hypothetical plot representing what we should observe if the feedback functions, but you'll notice some error bars on this plot. Now, these are, of course, representing instrumental limitations, but also uncertainty in planetary parameters. So the exact surface temperature, the exact surface pressure, any additional greenhouse gases, clouds, and so forth, these are going to affect the CO2 that we can expect for a given value of irradiation. So to detect and confirm that the silicate weathering feedback functions, we're going to have to be able to resolve a downward trend here, so for CO2 versus irradiation. But that may be difficult because of all the uncertainties that we're going to have. So this means that we'll have to observe a good enough number of exoplanets that we're able to marginalize over these uncertainties and effectively detect the feedback if it functions. So this is the goal of my current work that I'd like to talk a bit more about. So it's to try and figure out how many planets we would have to observe to resolve a downward trend. Because of course, if we'd need to observe about 100,000 planets, that's probably not going to be a feasible test, even with the biggest telescopes that we can expect in 50 years from now. Okay, so to answer this question, first I had to understand how this downward curve here changes as we vary uncertainty parameters. So here's an example for different values of surface temperature. So we've got the CO2 versus irradiation again. And if we go from green to black curve, so at a given value of irradiation, you'll notice that we gradually need more and more CO2 to maintain these higher surface temperatures. So that makes sense if the silicate weathering feedback functions. But what I'd like you to notice from this plot here is that surface temperature is going to add a pretty good amount of uncertainty into our measurements, because the shape of the curve changes quite a bit when we vary it, always within habitable conditions. Okay, so this was just some example of the kind of data that I obtained for answering how many planets we'd have to observe to detect a downward trend and so confirm the feedback. Now I'd like to lead you through my pretty simple statistical method that I built to answer that question. But first, we had to make some assumptions about just how much the uncertainty parameters, such as surface temperature, are allowed to vary. So we assumed some kind of probability distributions for each of them. So here's an example for surface temperature. The reason we're able to use this kind of Gaussian distribution centered around the value of the Earth is because if, and only if, a planet has a functioning silicate weathering feedback, its surface temperature should remain at around 290 Kelvin, plus or minus a range of uncertainty, instead of just using a uniform distribution. Now, if you're unconvinced by that, that's okay. We've also considered a much more pessimistic case where, for example, surface temperature takes on a uniform distribution, but more on that later. For now, let's take this as it is and go through the statistical method. So first, we choose a number of model exoplanets, say 3. Then for each of them, we're going to draw surface temperature values from the distribution I just showed you, and irradiation values from a uniform distribution. So we're simulating random exoplanets which may actually exist within the habitable zone. Now for this just proof of concept here, I'm going to consider that the only thing that can vary is surface temperature. Of course, if we were to consider the other parameters, we'd be drawing values from them right here from their respective distribution. Okay, so then we're going to compute the corresponding amount of CO2 using our data. So this is where the data comes into play. It's to initially build an interpolation function for CO2 as a function of the other parameters. And then we're going to add some instrumental noise to those CO2 values, depending on the instrument that we're assumed to use, such as Habex and LUVOIR. Because remember here, we're simulating a measurement of specifically just CO2 on a number of planets. And then we compute the irradiation versus CO2 slope for those 3 points. So here I've illustrated the slope as being negative, but it's important to realize that in some of these cases, it might end up being positive or very close to 0 because of our uncertainties. So when we repeat this whole process 10 to the 5 times, a fraction of slopes are going to be positive and a fraction negative. Of course, the more planets we model, the more slopes will be negative. So here, this slide illustrates the point I just made. So if we look at the purple curve here, it's for a low number of model planets, and you'll see a good fraction of the slopes are actually positive, which means when we observe too little planets, it's going to be difficult for us to detect the feedback. But the more and the more we observe, the more slopes end up being negative. So that's pretty intuitive, right? The more planets we're going to observe, the easier it's going to be to marginalize over uncertainties and potentially detect the silicate weathering feedback. But we had to figure out what's a good enough number of observations. So to do that, we defined the power here as the fraction of slopes with a p-value less than 0.05, so the fraction of slopes that are clearly negative enough. And we decided that power has to be 0.8, which means 80% of the slopes are clearly negative. So here, let's look at the optimistic case. To get a power of 0.8, we'd need to observe 11 exoplanets in the habitable zone of their stars. So what this means in real life is that if, and only if, the silicate weathering feedback functions on exoplanets, and we observe 11 of them, then we'll have an 80% chance of actually detecting it. So if 80% just isn't cutting it, we'll be able to adjust our results upward to have a better chance at detecting it. It just means we'll have to observe more and more planets. Now, you may remember that I mentioned also doing this for a much more pessimistic case. And so there it is. We'd have to observe 51 planets. Now, it's significantly more than just 11, but remember the pessimistic case here is extremely pessimistic. So we assume uniform distributions for a lot of the parameters. So the real number is somewhere around these two values, but most likely closer to the optimistic case. So these numbers seem pretty reasonable, but I had to understand whether or not we'd actually be able to do that with future instruments. So let's see here what we can expect to observe using a LUVOIR or a Habex-like instrument. Now you'll see Habex at the lower left corner. Habex is a lot smaller. It's a direct imaging instrument, but because of its smaller size and smaller cost, it's only going to be able to observe about 11 Earth-like planets, which means Habex is not ideal to make any kind of statistical studies, and we probably won't be able to test the habitable zone concept using such an instrument. However, LUVOIR A and LUVOIR B right here are much bigger. They might not be chosen because of their higher cost. However, they would allow us to have a huge scientific return for studying habitability of exoplanets in general. We'd be able to actually test the habitable zone concept that we keep on using with any new exoplanet discovery. So that's pretty encouraging, and it's a really good motivation for us to just really think about motivating direct imaging instruments that are of a good enough size that we can actually not only observe a few Earth-like planets, but increase their scientific return and test habitability concepts. Okay, so here are my conclusions. Thank you. Okay.
Hi, thanks for your talk. So I'm just curious how you think Venus fits into this. So it's got a higher radiation, yet it's got lots of CO2 in its atmosphere. It probably doesn't have a silicate weathering feedback because it's really dry. So how do you, planets that break the rules like that, what's your estimate of what they'll do to the number of planets you need to observe?
Yeah.
Because that'll add a whole nother noise source, it seems like to me.
Right. So I can think of 2 planets in the solar system that would break the rule. For example, we have Mars, which doesn't have a functioning silicate weathering feedback, but that's because it's just too small. And we likely won't be able to observe such small planets. So Mars-like planets aren't going to be an issue to begin with. Nor for Venus. Venus is a lot closer, so it's assumed to have gone through a runaway greenhouse effect. So before just blindly taking CO2 measurements, we'll be able to kind of just narrow down looking at just planets within the habitable zone itself. Yeah.
Bill Bodke, Southwest Research Institute. Oh, over here.
Oh, hi.
I was going to ask you about the Earth's case, because the current atmosphere we have is very different than, let's say, what we had more than 3.5 billion years ago. We may not have had plate tectonics back at that time, so silicate weathering may have been very different. How would that fit in with your scenario on habitability versus non-habitability?
Right. So it's true that so I think the Earth, for example, as a special case would add a bit of uncertainty in our measurements. However, the whole idea here is to observe enough planets that these kind of like cases, for example, Venus and so forth, don't really matter anymore. So if we look at the Earth throughout its history, I think its inhabited history would fit in within this test. But yeah, I'm not quite sure about even earlier than that. Earlier than that, it would, it wouldn't be good for the measurements, but within its inhabited history, I don't think that's going to be a problem.
One more right here.
Oh, yeah.
Hi, Jade. Very, very encouraging numbers. So let's say the number is between, say, 10 and 50 Earth-like planets. You assume a solar type spectrum, that is, we're thinking really about Earth-sized planets around a sun-like star.
Yeah. So that's what LUVOIR and HABEX would be looking at.
And we know some planets in the habitable zone, transiting planets in the habitable zone from Kepler, and maybe soon from TESS, but they won't transit sun-like stars in the habitable zone. Mm-hmm. So the bottleneck doesn't seem to be LUVOIR or the follow-up, but for me, I think the bottleneck really is the detection and the knowledge of these planets. Mm-hmm. Is there any idea, is there any follow-up mission of a super Kepler that would monitor, say, millions of sun-like stars so that we can actually detect our targets in the first place?
I don't think so. Actually, I think you would need LUVOIR in the first place. For example, James Webb won't be able to see these kinds of planets either. So, yeah.
We've got one more.
Oh, okay.
Of course, there's another way to break the CO2 rule, and that's by having technological civilization on your planet. So I would turn this around and saying that this is actually quite a nice way to begin to look for technosignatures, and particularly if you have a multiple planet system and some of those planets begin to look an awful lot like one another, even though they're at different distances.
Right. So actually, I was thinking a bit about that in this past month. So if the silicate weathering feedback functions, surface temperature should be regulated within the habitable zone. So it shouldn't just decrease as a function of the Stephen-Boltzmann law. So if we observe enough planets and we see some planets that are just like completely like different from the trend we can expect, then it might be worth looking closer at these to potentially detect technological signatures. Yeah. Okay.
Yeah, one more. I am invoking chairman's privilege here. So you mentioned the lower bound, you know, in response to the question about Mars, that Mars is too small. But my understanding of our uncertainties on the upper end of planetary size, involving what size planets could support actual plate tectonics that could produce a mixed planet that has both solid surfaces to actually do the weathering and then a liquid repository to receive it, may be very narrow. And so, you know, are we looking only then really at one Earth mass candidates, or is there a way to apply the same kind of signaling to planets that are much larger? I think that this is where there's a huge amount of uncertainty, and whether or not ocean worlds, you know, would present any kind of erodible landmass to produce this kind of signal.
Yeah, no, that's true. Yeah, I think we potentially have to be focused not just at planets that are closer to the Earth size instead of super-Earth, but maybe also at planets that are closer to the outer edge, just because it's going to be easier also to detect the CO2 itself. So but luckily it's also where we can expect a stronger negative trend. So yeah, we're gonna have to limit our measurements a bit. Yeah. Okay. Thank you. Oh.